All right. So welcome to thermodynamics class, and yes, any text comment? What you are talking about? My tutorial is class. Ah. So I don't know who you are talking about. So is this PowerPoint available yet? What does it mean? You did not get the this content, this lecture yet? It is already I think it's already open. The canvas is open. Can you tell me that you did not get it or you got it? I uploaded last week, and on Canvas, can you access the PowerPoint? Yes, you should. Just please tell me if you can't access, then I have to check it. What happened? All right. So did you go to the Canvas? Patrick, is it Patrick? So is it there? Oh, really? Just a sec. Just a sec. It should be there. It should be there. So that is from where I download now. So it is already, yeah, all are published. You see, all are published. The green button means all are published, and this is the tutorial problem. Everything is published. So this is the lecture 1. All are published. I don't know why you can't get it. Just a sec. Let me check with the student view. So now I'm a student. Oh, yes, you cannot. I don't know why. But the university told they already made it available to students. Let me check. Uh, uh, you see, just a sec. Published. It is published. Next week on, there is no tick. Yeah, so I cannot. So this is lecture 1. So if I click here,
I think click next to the lecture 1 material, big 2 tabs before that. So where it has
here
above the first one where it says lecture 1 material.
Okay, so this is the
And then
PDF,
the
this is the
three,
PowerPoint.
yeah, so on top of that, the 3 dots.
Okay, here?
On top of that?
On top, here.
Yeah.
And here.
And then publish it to students how you would publish it, I'm pretty sure.
There is nothing like published. So maybe only the share to commons. I don't know what is it.
I think the circle.
Oh, this is
publish.
That
yes,
one.
yes.
Okay, yeah.
Yes, I did it. Yeah. Now it is published. Can you check?
Yeah, I can see it now.
Okay, good. Sorry.
The whole module is though, so if yeah, I think it's all working.
did you get the lecture 2 as well? Like lecture 2, lecture 3?
No, because they still have the like little cancel symbol. So just when you
Oh,
want to
okay.
share
Okay,
those, you press it.
that I need a little more work and then I'll make available. So just
Okay.
let me check it
Yep.
because it is available here, but I need to click it here. But before I do that, I need to check a little bit and then I can do it. So just the week 1 and this lecture you just have. But I don't want to make this available to you yet
I
because
think you can untick it.
yeah, I can do
Yeah.
unpublished. Yeah, but it's a lot more. Don't download. So the because the tutorial is start from today. So if you access now, I don't know. It's up to you. You can download. Anyway, so that's done, and now you should start. Yes. So if you don't know me, I'm here at UTS since 2017. But before that, I was QUT for about 7 years, from 2011 to 2017 at the end. So it's about 7 years I was at QUT. And then I moved here. I did my PhD at James Cook University in Townsville a long time ago. It's 2009 I finished my PhD. And I usually teach fluid dynamics, heat transfer, and thermodynamics. So this is actually my expertise, my research expertise on this topic. And also I do some other research in some other areas. For example, the biomechanical engineering, this field. But I like the heat transfer, okay, related to heat. That is my expertise. All right. So anyway, from this lecture or from this subject, what you learn? No, a lot of students, I already announced you that please use your university username and password. Then I don't need to allow you again and again. So there are some security issues. Somebody using their personal email ID and these things to access this. So I should not allow you. So if you go like a Zoom UTS and go there, and if you join a meeting with the meeting ID, so I think you don't need to like request for like you don't need to be waiting room. You can directly join here. So I did not give any restriction. Well, I don't know why you are using the personal email address. Okay, so please use the your university email address. All right, thank you. And so after this subject, when you have finished the subject, what you learn? You will learn the steam turbine engine. Okay, so the Rankine cycle. So you will learn this system, and then you learn the gas turbine engine, the Brayton cycle. So this one you learn, and you will also learn the thermodynamic analysis of a refrigeration cycle. So these things you will learn when you finish this subject, and also the engine. Okay, the engine we use normally in the car. So this one you learn from this subject. So just talk about some assessment. So the lab report, the lab report is the weight is 25%. Okay, it's a group assignment on air compressor equipment. So this date is not correct. So this is the last year one. So I'll check it. I'll change it. All right. So and when before I upload this again, I'll replace this file with a new one. And also you can find this date in your the study guide. Okay. So it is not correct. So from this group assignment, you will get 25%. Okay, and there will be 3 quizzes. Each quiz will carry 15%. Okay, so that when you finish the thermodynamics properties, work transfer, you will have the first quiz. The second quiz is the first law of thermodynamics, and the third quiz will be the second law of thermodynamics. Okay, and the final exam will be 30%.
Sorry, I'm assuming the lab report due date's different.
Yes, it is. It is last year, 4th October.
Ah, sure, yeah. All right, cheers.
So not this one. So I'll change it. I'll change it.
Okay, thanks.
Yeah. All right. So now this is the book. I will mostly follow. Okay, and if you can buy this book, or if you can't, so this is the book. All right. So this is the book I mostly follow. And maybe sometimes we give you some problem numbers you have to find in the book. So it is wise if you can. I think it's the last year, this year, the same version. They did not change the edition, so it is the same edition. All right. So if you have like the old book, is okay. Or like a soft copy, if you can find any soft copy, that is, I think soft copy is cheaper. So if you buy the soft copy, that is also okay. And I think it is also available in the university library. So that's it about the book. Now the objective of today's lecture. So in this today's lecture, we'll introduce you the pure substance, what is called the pure substance. And also we can discuss about the physics of phase change process. So this is a very, very interesting phenomena. We actually learned maybe in the high school, but here we learn more. All right, and we'll also illustrate the PV graph, the TV graph, PT graph, and also the PVT diagram. That is a bit complicated to see it because it is a 3-dimension, P, V, and T. So the pressure, the volume, and the temperature. So this is actually 3D, and it's very, very hard to explain. Okay, but it is easy to do like a 2-dimensional, like a PV or TV or PT. And demonstrate the procedure of determining thermodynamic properties of pure substance from tables of property data. So as you know, when you have this book, you can get at the end from the appendix, you have a couple of data tables. So that is very, very important. Even your final exam, you need those data tables. And because it is an open book exam, so you can carry your book, not a problem. But I know maybe not all of you can buy this book. I can upload, or in my lecture slides, you can get this table. So you can collect those tables in your final exam. So that table is very important. Most of the time, we will use this table, okay, to get some solution. That table actually created based on lot of experiments, a lot of study, a lot of research, and after that they developed that table. And now when you do any like a simple mathematical calculation, we can directly use those tables. So I'll discuss your lab a little bit later. So don't worry about now. So now, what is pure substance? I think I should write something here if it is needed. Okay, the pure substance which has the fixed chemical composition throughout. What does it mean? It means, for example, a gas like air. So air actually has a lot of like hydrogen, oxygen, nitrogen, these things. But the chemical composition of this air is almost homogeneous everywhere. So that means we can still consider it is a pure substance. Okay, so nitrogen is surely a pure substance. And if you have some liquid, and if we have the liquid, the vapor state, that is also a pure substance. What you are talking about in the chat? ETS email is down and I could not reset my password. Oh, really?
Yeah, that was me. That was for I couldn't reset my Zoom password. That's why I'm logging in the way I am.
All right. Thank you. Now, but if you have like some liquid and gas, for example, air and water, so it is not a homogeneous. Okay, so it is not a pure substance. Okay, so now you understand what is pure substance. Pure substance is like the liquid, for example, the water. If you boil the water, then the water will become the vapor. Okay, so the water chemical properties and the vapor chemical properties the same. So we can consider both of these as a pure substance. But if you have like a half of the container is water and the rest of the container is air, then its total is not a pure substance. It's a complex or like is a different. Uh, they have different chemical properties, so they are not the pure substance. The pure substance is either it will be the same, either liquid, same liquid, or a liquid and it's the another state like the vapor, or sometimes the solid, for example, the ice and water. Okay, so they are the same chemical composition. So they are called the pure substance. Okay, but if we have, for example, water and if we give a little bit of oil, so this, you know that water and oil, they never mix. So that is not a pure substance. So that is different. Now, what is these three steps? So if you have any understanding of molecules, then it's good, you will understand. But if you don't worry. It's not much complicated. So you know that for the solid state, so we can always give example of water. Okay, if water has ice, you can see all the molecules are very regular. Okay, you can see on the left side this one. This one is very regular, organized. They don't move anywhere, just stay in the same place. All right, and it is very organized and very close together. So that is called the solid state. But when it is a liquid state, it actually starts moving. The molecules start moving, slowly start moving, but they follow some pattern. Okay, they are not scattered. They follow some pattern and they're very close to each other. Okay, so that is the liquid state. But in the vapor state, there it is like dispersed each other. Okay, so they don't have any pattern or anything. So they just go here and there. Okay, that is called the vapor state. So that is the molecules how they state in the different steps. So if we have a little bit of understanding of this molecular thing, then it is easy to understand. But it is actually normally is not very tough. So this is a video what I already told. So is just follow this one. Sorry, anybody is telling anything? Okay. So you can just what I've told until now. So there is a small video. So we created a small video and put it here just for your better understanding. Okay. So that is up to here. And now next the phase change process or pure substance. So I can just give you an example of using water. The total picture of water, then I can focus on this. If you consider water, what is its solid phase? So its solid phase is ice. Okay, and ice, the temperature when it becomes from ice to water, okay, that temperature is minus 4 degrees Celsius. Okay, the saturated temperature. So that is 4 degrees Celsius, or minus 0 degrees Celsius. Sorry, minus 0 degree Celsius water. Okay. Now, before 0 degree, what happened? So that is the ice state. And if you like heat the ice start melting. So when it becomes melting, so the temperature you will get always the same until the whole ice is melted. All right, and then start rising. The temperature start rising. If you still keep heating that ice, so that's become uh, 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 fully water. And if you start heating, so the temperature will rise. So temperature rise to like 100, and when it becomes 100, the saturated temperature of water, you can say it is as water to vapor, that is that. So if you still heat, then the temperature will not increase anymore. Okay, so the temperature will be the same 100, but it changes the phase. It from water to water vapor, and it will take maybe some time to convert this whole water into vapor. The whole time it will be the same temperature. So when this finished and it become the like a whole vapor, if we still heat it, then it will be superheated. So that vapor will get more heat. It will not condense. Okay, it will be like more vapor that time. So that is like the total story of three stages, three state of water. All right. So please, if you do some chatting, some private chat or something else, chat later on. If you have any questions, ask me here. Then I can check it. Otherwise, if I check all the time the chat box because it pop up that some new chat is coming, then it's not good. If you have some real question, you just put it there, and then I can come back to chat, and then I can discuss. Okay. Now, just consider here, we are not going back to the ice. We are starting from the water. Okay. So see the first picture. Yeah. So there are a couple of stages, about 5 stages or 5 states. So the state 1. State 1 is if we have, for example, some water with 20 degrees Celsius, okay, and with 1 atmospheric pressure. As you know that the pressure and temperature is very, very important. Okay, if we change the pressure, then the temperature will be changed to like convert from water to the vapor. Okay, so it is very, very important. Lot of chat going on. I'm not looking the chat anymore. Anyway, if we have 1 atmospheric pressure, that is the things when your water becomes vapor 100 degrees Celsius. So that is the state. But if you change the your pressure, so this will be changed. There is no not 100. It should be different. Should be either more or should be less. Okay. So that's why we have to either fix one and we have to vary the other one, or the opposite. Okay. So this is the state 1. But the state 2 is when you increase the temperature to 100 degrees Celsius. So that is called the saturated liquid, because after that it starts vaporization. Okay. So that is called the saturated temperature or the saturated liquid. And this is called the compressed liquid. Okay, we are compressing with 1 atmospheric pressure. Okay, so this is called the compressed liquid, and this is called the saturated liquid. Saturated liquid means when it is about to vaporize. Okay, at that last step. So that is the second step. And the third step is it's already started vaporization. As I said, when it started vaporization, then the temperature is not changing. It will be always like 100 degrees Celsius. Okay, so this is in the bottom, this is the saturated liquid, and in the up is a saturated vapor. Why it is a saturated vapor? If we stop heating it, it will condense. Okay, because the saturated vapor temperature is 100 as well. So now we can see how interesting it is. The same temperature of water and same temperature of vapor, but to convert it, it needs lot of energy. Okay, this is the energy we normally can use later on. The energy storage nowadays we are using even in our house for ventilation. For heating and cooling. So we are using it. For example, the PCM, the phase change material. The phase change material we are using at home in Australia, not very popular, but in US is very, very popular. So what we are doing, we are putting some phase change material, okay, on the ceiling, just above the ceiling. It is like 25 degrees Celsius temperature is become melting. So that means when your temperature is more than 25, it start melting. For example, in the daytime, when the sun is very strong and you have more heat transfer into the house through the attic, okay, so the PCM start melting. But as I said, it has a lot of energy. That means it takes long time to melt all. Until then, you are getting the same temperature, 25 degrees Celsius. So that means you are not using air conditioning, you are not using fan, but your house will be 25 degrees temperature. So, and in the evening time, when the sun goes, so you will get back from liquid to the solid state again overnight. And the following day is happening again. So that is a very organic way to cool your house, okay, using PCM, phase change material. So now phase change material is using a lot of places. Even sometimes in the car to cool the car or to cool the hybrid battery. So that is a very important place. The hybrid battery, you know that it is a very fast charging battery. If you charge very fast, it generates a lot of heat, and that heat can damage your car or that heat can damage the battery. So we need to cool the battery. So we are using this PCM. We are embedding the battery cell with the PCM, and then we are charging the battery, and then when it is charging, it's becoming liquid, and after that it's becoming solid again. So this is a very nice way to use this energy. So please ask me question if you have any question anytime when I just go through this one. Okay. Now, as I said here, so the convert from saturated liquid to saturated vapor, it has a lot of energy. We may need to convert it, or if it is like opposite way, we can get back those energy from there. So it has a lot of application, as I just mentioned, two things, in the house and in the car. Now, when your whole water becomes vapor with 100 degrees Celsius, so that is called the saturated vapor state. So that is state 4. Okay. So this is about to condense. So if you don't further heat, it will condense and you will get the water back. Okay. Now superheated vapor. If you heat more, for example 300 degrees Celsius, you are getting it will not condense. When to make it condense, you need to reduce the heat. The heat is one kind of energy. So you are giving the energy, and you are changing the phase of one state to another state. Okay. So this is like a 4 steps. So this is state 1 is called the compressed liquid. The state 2 is the saturated liquid. When the liquid in the terminal stage, okay, to vaporize, just that step is called the saturated liquid. And then when it start vaporization, and then some part will be liquid, some part will be vapor. So that is called the saturated vapor, because that saturated vapor has the same temperature as the water. So that means they both are the saturated state. And then step 4, when your whole water, okay, so become vapor. So that is the step 4. And step 5 is superheated vapor. So this is this is a very nice figure. I always like this figure. So you can see the whole entire process from 1 to 5 steps. If we reverse it, we'll get the we have to cool it and we can get the reverse process. So this is reversible, okay, and we can get everything back, but we are getting huge energy from there. Okay. Now see here. See here. I forgot to tell you, when your when it is a liquid state and you are still heating, what happened? So it will actually expand. Expand means the volume increase. Okay, the volume increase, and that increase is a bit slowly, not very fast. For example, if you have like this is a container. Okay, so this is the fluid. For example, this is your 30 degree Celsius, but when you have like this, so maybe it is 90 degree Celsius, so you have a little bit more volume, so this volume increase. Okay, so volume will increase, but when it becomes this is this is called the compressed state, the liquid phase. So this is called the saturated liquid. Okay, so this is the saturated liquid, and this is the saturated vapor. Okay, and this is the superheated state. So saturated liquid and saturated vapor, you can see both the same temperature, 100. But from here to there, volume. So this is actually volume. The bottom is the volume. Okay, and this is the temperature. So the y-axis is the temperature. X-axis is your volume. So that means when you are heating the water, so the water temperature rises. You see, the temperature rises from 20 degree to 100 degree here. At the same time, your volume is changing. You can see how much volume is changes. So this amount of volume is changes. Okay, from here to there, and you are still heating it, but the temperature doesn't change, because they are changing the phase from liquid state to the vapor state. So that's why temperature is the same. So that is the beauty of phase change material. Okay, so and then until here you are getting the same temperature, but you are getting very volume expansion. Okay, here, and then is a superheated. But when it is superheated, you can see like all the molecules are like going here and there. You can see It's called the Brownian motion starts in there. So there is a lot of complicated things happening there, and it's still expanding. Okay, so that is called the superheated state. So you understand? Any question in here? So that is actually all the time we'll use this PV diagram.
Raincoat ako. Raincoat.
So any questions? Anybody has any question until now? Okay. So no question. Let me just. So I'm just repeating one more time. So here we have a liquid which has 20 degrees Celsius, and then we are increasing the temperature. So it is expand, slowly expand, also increase the temperature, and is going up to 100. So that is the saturated temperature for liquid, and becomes the saturated liquid, because this liquid is about to vaporize. So it is here, and then start vaporization, and then it is a mixture of saturated vapor and the liquid. Okay, so this is step. Okay, so here is called the saturated vapor, because that is the maximum. There is no liquid left here, and that is the actually the volume increase a lot. And then if we are still heating it, then it is in the superheated state. Okay, and going up to here. But you can see is everywhere we have the same pressure. We are not increasing the pressure. Pressure is the same, 1 atmospheric pressure. If we change the pressure, it will be changed. For example, here you can see the video. Okay, in the video you see the blue, and then becomes like change in the color. You can see from here to there. So this is the saturated liquid, and then this is the middle state, and we have the saturated vapor here, and then becoming the superheated. So this is the superheated. Okay, so that is your 1 atmospheric. When we are heating it, keep heating, so we are getting this one. But if we change the pressure, what will happen? Instead of 1 atmospheric pressure, if we give like a 2 atmospheric pressure, what happens? So this figure is given, this one is 1 atmospheric pressure, 1 atm, and this one is 2 atm. Okay, so you see the change. Maybe if it is 100, it is not 100, something more than 100. So if you increase the increase the pressure, you need more heat to vaporize. Okay, so the more you pressurize, the more heat you need to vaporize the water. So that is the relationship between the temperature and the pressure. Okay, to change the phase. So that is very important. There is a lot of other curves. I'll show you later one. So this is the video until now, what I just told you. So you can listen here. Let's play one, see how it goes. All right. So that is the video. If you watch the video, you can learn what we have discussed here. You can get some more information as well. Now, so this is the table 3.1, the saturation or the vapor pressure of water at a various temperature. Okay. Now see the temperature 100. When the temperature is 100, the saturated pressure is 1 atmospheric pressure, 101.3 kilopascal. Okay. So this is the saturated pressure. Now you can see if it is a 150 temperature is more, you need more pressure. Okay, 475.8 kilopascal. But if you have less, like 50 degree, then you need this pressure. Okay, if you like a -10, you need very, very small pressure. Then you can get the change from liquid to the vapor. So this graph, this figure table is very important because sometimes you need to get this value. What is the saturated pressure when the temperature is 20? You need this 2.34. Okay, so these table all are created based on some experimental results. Now there are some definition here. What is latent heat? Okay, so this definition is we need to calculate some thermodynamics properties. Okay, so latent heat is the amount of energy absorbed or released during a phase change process. So that is called the latent heat. So the latent heat of what is called the vaporization or latent heat of what is called the liquidation. So from solid to the liquid. Okay. So that has some latent heat and there is some latent heat. So two state has two different latent heat. Okay. So the latent heat of fusion. So that's called the latent heat of fusion. That is the amount of energy absorbed during melting. Okay. When it's become from solid to the liquid, like ice. So the amount of energy absorbed during this melting time, it is equivalent to the amount of energy released during the freezing. So it's both the same. So that should be the same. The amount of heat it needs or the amount of energy it needs. And when it go back to that state, you need the same, they release the same amount of the energy. Okay. Now the latent heat of vaporization. The amount of energy absorbed during vaporization and it is equivalent to the energy released during the condensation. So the amount of heat or the amount of energy it needs to convert the water to the vapor, and you get the same amount of energy when it comes back from vapor to the water during the condensation. You'll get back those energy. So it is very important that the magnitude of the latent heat depends on the temperature or the pressure at which phase change occurs. Okay, so if you change it, you will get a different amount of this energy. Okay, that is also very important. For example, you can see at 1 atmospheric pressure, the latent heat of fusion of water is 334 kilojoule per kg. The latent heat of vaporization is 22, 2257 kilojoule per kg. So that means the atmospheric pressure and thus the boiling temperature of water decrease with the elevation. And here you can see this table from here. Okay. Now this is the property diagram for phase change process. So I want to explain this one as a bit. Okay. Now in the vertical axis, it is the temperature, and the horizontal axis, it is the volume. Okay. Now see here, when, for example, we are doing like when it is the pressure is 0.01 megapascal, that time this the chart is like that. Okay, so here you have the liquid phase, here the saturated liquid, and here you have the mixed, okay, of saturated liquid and saturated vapor, and here you have the saturated vapor and then superheated. Okay, so the volume change from here to there is the highest for all the pressure considered in this case. Okay, so that is the maximum volume we are getting for 0.01 megapascal pressure. Now, if we increase the pressure to 0.01, you need more temperature. You see, here temperature is for here temperature is increasing, because as I said, the more pressure you give, the more heat you need. Okay, so that is the temperature, and it also needs less volume. Okay, so less volume, it starts superheating. So if you change this or increase your pressure to 1, you need more temperature, like and also less volume. Okay, then 8, less volume, 15, less volume, but at 22.06, this value, it is actually very, very fast. It's going there and then going back. So that is like a saddle point. Okay, just only one point it has. It does not have more volume change. Okay, just start superheating. And if you give more pressure, it will not vaporize. So there is no phase change happening if you have more pressure than this. So that's why this is called the critical point or critical pressure. So for critical pressure, you have the corresponding temperature is 373.95, and the critical volume is 0.003106 meter cube per kg. Okay, so did you understand this one? When you vary the pressure, how this volume and temperature change? So that means when you are increasing in the pressure from here to there, increasing the pressure, we are also increasing the temperature. Okay, and then but reducing. Oh, sorry. Yeah. So the more pressure you are giving, the more temperature you need to do that. But at certain time when it's coming here, then no further volume change you are getting. Actually, is all the same state like a liquid state. It is not changing. Okay. So now if we connect all these points here, 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 then we'll get a dome shape curve. So that I'll show you later on. So now for pressure less than the critical, so if we call it as critical pressure, so this one, if we call this one as a critical pressure, then less than the critical pressure, we have phase change. Okay, but more than the critical pressure, there is no crescent. Okay, the same step. So this is this curve, and the second curve, yes, this is the one. I told you, if you add all these points here, yes. So you see, this is the curve. So it is very systematic. It is not very complex. So this subject is not complex at all. So if you follow my every lecture, at the end you will be Superman in thermodynamics. So it is very, very easy to follow. Okay, step by step is connected. So you need to just follow it. If you miss somewhere, you'll be messed. Okay. Now, another important things I want to mention here is sometimes I tell some important things during my lecture. So just don't follow the lecture video. Some people, and sometimes the lecture video doesn't work. Even I'm recording. Sometimes I don't get the recording back. There are some technical issues, so we'll be missing. So that's why I'll suggest you to attend the online lecture, because it is easy for you, even using your mobile or any device, and so that is very good for you. I give very important information sometimes in the lecture, during my lecture. I normally don't announce. Okay, so that's why it is important if we attend all of my lecture. Okay, and sometimes just interact with me. Otherwise, I'm feeling that I'm teaching some invisible things. I have nobody in front of me. I hate this. I love to teach in the class where all the students will be there. I can communicate with them. I can go to them. I can discuss with them. So that I very much I love. But this pandemic changed a lot. Hopefully next semester we'll get you back. All right. So please just sometimes speak up and ask some questions, so that I feel that I'm not alone. Anyway, what I was talking about is those points I said. If we connect those points, then we'll get a diagram. Okay, the dome shape diagram. And it is actually the same what we have done before. So that is the saturated liquid line from here to there. Okay, saturated liquid, and then from that step, this is the saturated vapor line. If you go here, you can see this all is a vapor point, saturated vapor, and this is saturated liquid. Okay, so they get this connection, then it will be easy to understand. But if you only see that curve, sometime you will be lost from where it comes, But if you see this figure, then easy to understand that one. We can divide this part. So left part is liquid, right part is vapor. But it's not all vapor, but it's just some vapor, some liquid. So, but here after this point, all are vapor. So this is the saturated vapor line, and this is the saturated liquid line. So still we are doing the temperature versus the volume curve. Okay, the temperature versus the volume curve. So that means for fixed pressure, the same line, but if you change the pressure, we are getting from P1. If the P1 is greater, if P2 is greater than P1, we are getting here, and we are getting here. Okay. So that means we are changing the pressure, we are getting different saturated these vapor points and saturated liquid points. Then we are getting the smooth curve. Okay. So this actually, without further doing an experiment, if you have this curve, you can easily get the point based on any point you choose for this this pressure. What is your the saturated vapor volume, and what is your saturated vapor temperature? You can easily calculate for different pressure. Actually, you have a table for that, so it's easy to do that. I'll show you later on. Okay, just here I want to stop, and I want to ask you one question. Some feedback. Is it okay? I'm going very fast or slow, or do you understand what I'm talking about? So you have any comments? Can you give me some comment and feedback?
Well, your speed's all right.
Yeah, I think it's good.
Good. All right.
We're all
So-
here, by the way. We haven't for you. I know you're feeling like we're not here, but we are here.
Good. Thank you. Thank you. Now I'm feeling not I'm not alone. Okay, that's good. Yes, it is perfect. Thank you. Thank you. Now what we'll do? It is a pressure versus volume. So that is different. Okay. Now we'll change the temperature. How to do that? So we are, for example, when we have for temperature T1, if we change the pressure, we can easily do that. Suppose if it is like a piston, like a cylinder, and we have all this pressure on here, right? And then we can take one after another one, and then we are decreasing the pressure, and we are measuring the temperature. Okay. Sorry, we are measuring the volume. Sorry, we are measuring the volume. So reducing the pressure. So here is the pressure. We are reducing the pressure, and we are calculating this volume. You can see here. Start from here. Maybe we have some value of the pressure, and then we are decreasing. We are taking one by one from here, and then we are reducing the volume. The volume is increasing, not reducing. You can see, but it's very, very small. You can see the corresponding. So this is the decrease, increase the volume. All right. So, and then the next one, the another one. Okay. For next one is T2 temperature, which is greater than T1, is here. Okay. And then we are reducing the pressure. It's coming here and here. The saturated liquid, and it is saturated vapor. Okay. Still it is a saturated liquid line, and that is saturated vapor line. And at the end here, we are getting the critical point. So both places, the critical point the same. Either you use the PV or like a TV, the same. Okay. So this critical point is the same. Right? And this, after this region, this is called the superheated vapor region. And this is actually the saturated one. So saturated means it's about to condense. If you don't further heat, okay, then it will go back. It will come back this way. Okay, so that is the process. So both the different, but the thing is, for heating one, you can see the heating one. That is, yeah. For heating on, we have like for different pressure. So it is increasing. Temperature is increasing, but here is pressure temperature. Sorry, the for fixed temperature, the pressure is reducing. So that is the importance. It's just if you increase the temperature, you need more pressure. If you increase the pressure, you need more heat. So that is the relationship between the temperature and the pressure. Okay, and we have discussed further here. Yeah, so you can, when you see this video, Okay, I'm not more. So you can have a look when you get time. So what I just split it different section, and then we made the video. Okay. Now this is a very interesting diagram. I like this diagram very much. Okay. So this actually classify all these three steps. Okay. If we consider, for example, water. So this is the solid phase here. So this is the T diagram. That is the pressure. This is the temperature. Okay. As I said, if the temperature increase, the pressure increase. So this is the curve. So that is generally the case. Okay. But the solid, we are always giving the example of water, but there are some other liquid as well. So they don't behave like the water. So that should be different. Okay. But if it is the water, so this is the solid phase, this is the vapor phase, and this is the liquid phase. Okay. So now these three curves. So this is the curve for the vaporization. So up this side is vapor, this side is liquid. This is the sublimation line. So this is actually the line between the solid state and the vapor. So normally there are some other things in between. So it is a long one. So now here what we can see, if the substances that contract on freezing is this, and substances that expand on freezing. For example, ice. Ice actually, it actually increase the volume when it become ice from water, isn't it? The volume expands. So the melting line is this. But there are some other things that actually contract on freezing. So this is this line. Okay. So that is very much we just discussed in this video, just only for this diagram. Yeah, this is the most complex things. I don't want to spend time on that because it's a very like you have to be like a three-dimensional mind to understand this figure. Okay, so this is actually PVT diagram all together. Okay, so this is the temperature line, the specific volume, and the pressure. Okay, so the three dimensions of three sides. This side is temperature, this side is a specific volume, this side is the pressure. And then what is happening here? All things are explained in one diagram. And I got a very nice video on the YouTube, and I just put it here. So this one, they explain this one very nice way. Okay. So if you see this video, you will understand how they are doing. It's exactly the same thing here. So they just did the video. It is actually in IIT India. So this professor, he explained it very nicely. That's why I just put it here. If you understand, if you want to understand more from here. But I don't think that that is very important for you to understand. 2D is better. Okay. The 2D we understand better. But if you want to see all together in one place, then you can see this one. Okay. Now there is another important physical property. It's called the enthalpy. So in thermodynamics, enthalpy is very important. But heat transfer, no. So I also teach heat transfer. I maybe next semester you may take the heat transfer. Next semester I'll be teaching heat transfer and also thermodynamics. Generally the heat transfer is in the both semester, this semester and the next semester. But this semester they stop providing the heat transfer, so it will be on the next semester. So I'll be teaching the heat transfer. I think most of you will do that because this is the prerequisite for heat transfer, right? So you have to finish thermodynamics, then you can go to the heat transfer. So the main difference of heat transfer and the thermodynamics is the thermodynamics actually is some static things or related to energy, very static. And heat transfer is dynamic with time. Okay. For example, like a cup of coffee. So cup of coffee, if we analyze the thermodynamics, we can find out how much energy it takes to heat the coffee. Okay, how much energy it needs. So in heat transfer, we don't need to know that. In heat transfer, we will measure. If we have like a cup of coffee, and if we keep it here, how long it will take to reduce the heat, and it becomes like a normal temperature. So that heat transfer is important for the heat transfer subject. And when you make some design of MOM, we need to study the like heat transfer, because we need to know the property of these things. Okay, how insulated it is, what kind of material we need it to reduce the heat transfer, isn't it? Because you are going to the office in the morning, you are taking a cup of coffee in the car and you are having it. So if it quickly become cold, you don't like it, right? So you need a longer time, how long it can keep hot, so that you can drive like half an hour, you can have a little coffee when you are driving. So that is very important to calculate the rate of heat transfer in the heat transfer subject. But here in thermodynamics, we don't need it. We need to get some information how much energy it needs. Okay, that is the main difference. So a lot of students, they just think, what is the difference? Because they both are dealing with the heat. So what is the main difference? So this is the main difference. So this terminology, the enthalpy, that is important in thermodynamics, but we never use in heat transfer. Okay. So what does it mean? So this means, so this is a combination of property, like u is not velocity, be careful. Okay. So u is, so this energy and PV energy, this is the heat, and this is PV, P is the pressure, V is the volume. So these two terms together make a separate term, we got is all together. Okay, the combination of these two is a one term, we call it H, and this is called the enthalpy, and that is actually very important if you study thermodynamics. Okay. Sorry, what was U? Okay, that is the energy, the heat, how much heat is needed. Okay, the heat. So that is that energy. This energy plus P and V, pressure at the volume. And you can see, if you get like the product of pressure and the volume, what you are getting here. So this is the pressure kilopascal, and volume is MQ. This is the kilojoule, equivalent to the kilojoule. So this combination of these things we need to know. So this is the total enthalpy, and this is the like normal enthalpy. Now the saturated liquid and saturated vapor states. So when it is like a combination, so then we have sometimes some problem of analyzing. So if it is like in one state is easy, but if it is a combined one, some part is liquid, some part is vapor, so it's not very easy. So we need to do some technique to get it. Okay. So now see here, VF, which is the specific volume of saturated liquid. Okay. So this is actually the middle, increasing, middle, and increasing again. So in the middle one, when is the saturated state of the liquid. Okay. So this one and your the vapor as well. So here we have both the specific volume of the saturated liquid and the specific volume of the saturated vapor. I can draw a diagram here that is easy for you to understand. So if we have like if we heat it, so we are heating here, and now we have, yeah, this is a vapor and this is your liquid. Okay, so it's still two steps. So then the Vf is the specific volume of the this liquid Vf, and Vg is the specific volume of the saturated vapor. Okay, and Vfg, that is a very important thing. Vfg is the difference between the Vg and Vf. Okay, so remember Vfg is equal to Vg minus Vf. Okay, so these three things we need. We have some mathematical calculation later on, and that time we need it. So come back to here. So this is the specific these things. You can see the temperature when it is 85 degrees Celsius, the saturated temperature. We have the saturated pressure for this one for melting vaporization is 57.868. That is the saturated pressure, and then the corresponding saturated liquid volume is this, and the saturated vapor volume is this. Okay, this is already you have in a table, so you can easily get this one from a table once you know the saturated temperature and the saturated volume. Okay, so you can, from the table, you can easily calculate it. So there is another table is called A5, that is the saturated properties of the water under pressure, and that is water under temperature. So this one is under temperature. So this one is under temperature. There is another one for different pressure, we are getting the saturated temperature one. Okay, so now the enthalpy of vaporization. So the amount of energy needed to vaporize a unit mass, remember, a unit mass. Okay, the amount of energy, how much energy you need. The amount of energy needed to vaporize a unit mass of saturated liquid at a given temperature or pressure. So fixed temperature and fixed pressure. How much energy is needed to vaporize a saturated liquid per unit mass? So there is no mass, there only one. So the mass value is one. So that is called the enthalpy. Okay, so it represents the amount of energy needed to vaporize a unit mass of saturated liquid at a given temperature or pressure, and it decreases as the temperature or pressure increases. That is what we have found. Okay, and becomes zero at the critical point. That is what it found like this. So you see initially is very big and slowly decreasing. At the end is zero at the critical point. Okay, that is called the enthalpy. Now there is another what is called for the mixture, the saturated liquid and the vapor mixture. We have another important things that is called the quality. This time, the quality. This quality is needed sometimes. If you don't know the mass, then you need to know this value of the quality. Okay, to calculate some other thermodynamics properties. So this, what is quality? Quality is the ratio between the mass of the vapor and the mass of the total. So vapor and the liquid, the total mass. That is called the quality. Okay. So if it is like vapor is all over the system, it's all become vapor, then it is 1. So you can see the quality is between 0 and 1. So 0 is the saturated liquid Okay, 0 means when the vapor is 0. The top is 0 means 0 by total volume is 0. So that is your liquid phase. When a vapor convert all, so that is the total mass is the same. So that means is 1. So 0 and 1. So when is 0 is the liquid. When it becomes the vapor, whole mass is vapor, and it becomes 1, and that is the vapor. Okay. You can see here the saturated liquid line and the saturated vapor line. And then you can see here the saturated vapor and saturated liquid. So this X is very, very important for some cases where you don't know the mass. And if you know X, then sometimes it's easy to get the mass of some other thing. For example, is given 10 kilo of water, and you heat it and it's vaporized, and some state the X is something like 0.5 or 0.6 or something. Then what will be the volume? What will be the mass of the vapor? So it is easy to use this formula to calculate that. Okay. So you understand the quality? Okay, the quality is the ratio between the mass of the vapor and the mass, the total mass. Okay, that is called the quality. And quality is zero when the whole system is water or liquid, and it is the 1 when the whole system becomes the vapor. So that is the two extreme cases. And in between is the 2 steps, is the mixture. All right. So you can see the mass, total mass equal to mass of the liquid and mass of the vapor, which we define by mf and mg. Okay. So you can see F means fluid, G means gas. You can remember that way. But we call it, this is liquid and this is vapor. So now there is another one thing is saturated vapor and the saturated liquid volume. We call it some average volume, saturated liquid and vapor mixture. There is some called some other average volume. So a two-phase system can be treated as a homogeneous mixture for convenience. We just consider it a homogeneous mixture. So this is some maths here. So don't scare of this. It's not very tough, very easy. I'm just going step by step, then you will understand. So this is the volume. Okay. So the total volume is your volume of the liquid plus the volume of the gas. Okay. So this the volume. And now if we multiply the mass, then we are getting the total volume. So this volume is saturated volume, and if we multiply with the mass, we are getting the total volume. Okay, and then the mass, if it's the total mass, then it's empty. Empty is called the total mass. Okay, and the total we can call it the total saturated volume of the mixture. So that's called the average volume of the mixture. So now if we put this value here, we are getting from here to this, and we are getting this, we are getting this. So that means Vf is become mf Vf, because we have to multiply, because it's a unit mass. So you have to multiply the to get the total volume. We need to multiply with the small volume by mass to get the total volume of the liquid and the total volume of the vapor. Okay, we have to multiply the mass. Okay, so we get this. Now from here, as you know, that mf mt is equal to mf plus mg. Now mf is equal to mt minus
Yeah,
mg.
but yeah, the whole building is too much.
Sorry?
11.
All right. So this one is MF. So this is that. MF equals to MT, the total mass minus the vapor mass. So if we subtract from total to the vapor mass, we will get the
Coming
liquid.
like 30.
Looks like a
I think
police.
she's left her mic on or something.
Yeah, looks like a police walkie-talkie. All right. Now we are putting this value MF. So this MF is MT minus MG. If we put this on here, we are replacing the MF with MT minus MG. That one we get it from here. Okay. We put it here, then become this. Now, if we multiply, no, you don't need to multiply. If we divide this both sides with MT, what will happen? So this MT, this MT, this MT, this MT. So that means it's cancel out. So only V average. This MT, MT cancel, that is 1. And this MG by MT, that is our quality X. Okay. So they are getting X here. Times VF plus, so MG by MT, this is also X. So now it looks like some equation, right? So we are converting slowly to some equation. There the equation. Now it should be plus, not equal. Isn't it? The average, just a second. On BF, this is BF plus X VFG. Yes. You know why this plus? Because if we write this on this way, so that means if we multiply this VF inside, there should be VF minus X VF plus X VF. Now VF, and if we this is VG. This is VG. Now VF plus, if we take the X outside, then it is VG minus VF. Okay, the VG minus VF. What is VG minus VF? I just showed it here. Yeah, VFG. So this is your VFG. So VF plus X VFG. So that is what you got it here. Okay. So that means V average equals this. Oh, I already showed it here. Yes, it is here. It is given here. So now it is easy to calculate the X. So X is equal to, what is X? So that is your V average, this one. So X is equal to V average minus VF divided by VFG. So this is the formula to calculate this one. So this is our X, right? So if we take this on left side and divide it by VFG, so that will give you the X. So this is it's just taking left side, right side, and divide something. We are at the end we are getting this one. So that means generally what will happen is previously how we calculate this X, we calculate the ratio of the mass. The ratio of the mass of the vapor and the ratio of the mass of the like the total mass. Sorry, the total mass. The ratio of the vapor mass and the total mass, that was the quality. But now we converted it to the volume. That's what I said. If its mass is not given, if X is given, then we can easily convert it to mass if it's needed. Because in the exam sometimes we ask you to calculate the mass, but mass is not given. So this is the way you have to calculate the x from this formula. So that will be given, or from the table we can get this one, and then you can easily convert it to x. And when you get x, it's easy to get the mass. Okay. Generally, the total mass is given. Maybe 10 kilo water, 20 kilo water is given. So then the vapor state you can easily calculate. So U is the energy. U is the energy, heat energy. So here is not U. It is here all V, the volume. The different letter. Somebody asked that. Now, what is this? So this now from this equation, this is very important equation. So now this equation we can generalize it. We can easily apply this on for this energy. From this volume, we can apply to the energy. We can apply to enthalpy. Okay, the same concept, the same formula. If we replace the volume by energy, we can get this one. And if we replace the volume by enthalpy, we can use this one. So that is the general form of this equation. So if we know the general form, we can easily convert it to either enthalpy or volume or energy. So we can use anything. So this Y will be either V or U or H. That is the general form. Okay. So there are some pictorial figure here. So from the curve, okay, the dome-shaped curve, what we have is, here is a saturated liquid point here, is saturated vapor point here, and then this is the total volume. Okay, the total volume is this from here to there, the total. But from here to there, that is your the total volume minus. Okay, so Vg is from here, right? So Vg from here to here, and then Vf from here to there. So that means we just subtract this one. So this subtraction is giving Vfg. All right. So this is the way, and this is the x. X is the AB. Okay. So AB divided by AC. Where is C? I cannot see. Sorry, where is AB? So AB is here. So if we have average volume, it's somewhere here. So that means this is called AB, this is called BC. So that this ratio, okay. So this is the ratio of the liquid, and this is the ratio of the vapor. So that is to mass. So that mass is giving us this quality. Let me check some comments. What does letter V present? Is there any difference between the upper and lower V? Yes, yes. Upper V is the total volume, and lower is the lower. So that's the saturated volume. So to get the upper volume, you have to multiply with the mass, and then you will get the capital V. So there are some video for this one. I put it here. Now I want to solve two problems. Okay. So I want to solve two problems. What is the time now? 10:35. Yeah, we still have some time. We just solve two problems. It's a very, very simple problem. We have a problem. A rigid tank contains 10 kg of water. So 10 kg of water. So the liquid mass is given. Excuse me. Excuse me. Water at 90 degrees Celsius. Okay. So if 8 kg of the water is in the liquid form, so the liquid mass you already know, and the rest is in the vapor form. Okay. So 2 kg is the vapor form. Okay. Now determine the pressure in the tank. You have to calculate the pressure and the volume of the tank. So these two things we need to calculate. So if it is given here. For example, the temperature of the system is 90 degrees Celsius, and you know that if it is a 1 atmospheric pressure, it shouldn't vaporize. So that means pressure should be lower than 1 atmospheric pressure. So that means we need to calculate that pressure. Okay, that pressure, we already from 10 kilo of water, we are getting 2 kg of vapor, okay, and 8 kg of saturated liquid. So this is the problem statement, and if you draw the curve, it looks like this. Okay, so here is the 90 degree. It's already, because it is already started. This is saturated one, already started. So it is going this way, and then the vapor is here, superheating is here. So that means, what is the corresponding volume here? What is the corresponding volume here? So it is easy to get. If we see this curve, this table, from this table, so we have, who is coming now? Very left. Anyway. So it is a 90 degree, right? 90 degree. Yes. So this is the table A4, saturated water. That is the temperature table. So the one is temperature table, one is pressure table. Okay. So this is the temperature table. So for 90 degree temperature, okay. So what is the saturated pressure? 70.183. So that is the saturated pressure. You already got the answer. You already got the answer from the table. Okay. Now what is the corresponding VF and VG? Okay. So this is a VF is 0.0016, sorry, 0.001036. 0.001036, and the VG 2.3593. 2.3593. Okay, so you get it from the table, or sometimes it's given in the problem. Okay, so now to get the pressure is already you get the pressure from the table, so you don't need to calculate. You can directly get the saturated pressure from the table. Now to get the volume of the tank. So how to calculate the volume of the tank? So now the volume is VF plus VG, right? The total volume is the volume of the liquid plus the volume of the gas. So now we have to get it like a mass. So mass of the liquid, VF, plus mass of the gas, VG. Okay. So now what is the mass of the liquid? Is 80, right? No, not 88. Sorry. 8 times. So the VF is 0.001036. Okay. Plus mg is 2 times 2.3593. So that will give you 4.73 meter cube. Okay. So you are getting this value. This is a very easy problem. Okay. So this problem is very easy. To calculate the pressure, you don't need to calculate calculate it. It's already in the table, and the volume, you have to calculate this way. Specific volume here. I think, yes, you are right. It is the specific volume. Can you find the pressure again? Pressure is from the table. I already showed you. Okay, let me show you. Yeah. Yeah. This is the 90 degree. As I said, it is given 90 degree temperature. So for 90 degree temperature, so this is the pressure is given, saturated pressure. Okay, so this is the saturated pressure, which is 70.183. That is the way we get the pressure. We have a lot of other things like entropy, like enthalpy, like some internal energy. So we have a lot of things here. So when you need any properties, we can use this table to get it. Okay. So that problem is explicitly calculated here, and we actually did some other method. Okay, we actually did two methods using quality. If the mass is not given, so we also use, so you can see this this video. Yeah. In this video, we actually mentioned, yeah. Yeah. Oh, so this is the like this method. So I'm not showing it here because that is very easy. So when you see the video, you will understand what is the another way to calculate this volume. Okay, but because the mass is already given here, so we are not worried about that. So the second problem is an 80-liter vessel contains 4 kg of refrigerant 134A at a pressure of 160 kPa. Determine the temperature, the quality, the enthalpy of the refrigerant, and the volume occupied by the vapor phase. So these 4 things you need to calculate: the temperature, the quality, the enthalpy, and the volume. Okay, occupied by the vapor. So the vapor volume you need to calculate. Okay, so remember this one. This one is given. So now the pressure is given 160, and the mass is given. The total mass is given 4 kg. Okay, so this is a pressure versus the volume curve, and you can see when the pressure is 160. So this is the saturated liquid here, and this is the saturated. The vapor, where the temperature is minus 15.360 degrees Celsius. In this temperature is start vaporization, even in the negative temperature, because of the pressure. Okay. Now the corresponding value of the volume of both liquid and vapor is already here. We get it from the table, or maybe it is given. And this is the enthalpy. You can, if you go to here, you can see. So this is the refrigerant 134A pressure table. Okay, exactly that table. So now the pressure value is, the pressure value is 160, right? Okay, so you know we got the VF, VG, and also we need the saturated liquid enthalpy and the vapor enthalpy. So these two values you see here, 241 and 31. can see here 241 and 31. So this value you can get it from the table. Now we need to calculate the temperature at first. So before of doing that, we need to calculate the specific volume. So the specific volume is so small v, which is big V by mass, which is, so we have 80 liter. No, yes, 80 liter. Sorry. 80 liter means if we convert it to meter cube, it will be 0.08. 08. What happened? Meter cube divided by the mass is 4 kg. Which is 0.02 meter cube by kg. So that is the specific volume you calculate here. And the other things you already got it from the table. This is the things you need. Okay. Now, if you here and if you just compare, this is the volume we calculated, okay, and this is the volume here. So just a sec, how can I do that? So this V, sorry, not equal. If we just represent in an inequality form, it will show you VF, V, and VG, isn't it? Yeah, in between that. So our calculated specific volume lies between these two tabular value. Okay. So because it is that is between that means it confirms that it is a standard mixture region. Okay, so this is the way sometimes you need to think about whether we can use the mixture formula or not. So if it is between these two values, then it is a standard mixture, and then we can easily use that formula. So number A, temperature, the saturated temperature at a given pressure, 160, right? What is this? You already know. Minus 15.6 Celsius. So minus 0.6 degree Celsius. So one is already done. We get it from the table. Okay. The second one is the quality. So the quality. Yes. So B is the quality. So X is your V minus Bf divided by Bfg. Okay. So the V we already know 0.02, 0.02 minus Vf we have 0.0007435. 7435. Okay, divided by Vfg means the difference between Vg and Vf. So Vg is 0.12355. 0.12355 minus 0.00074. So it is in the video, next video. So that's why I'm not doing very neat and clean way. So you can see from the video I did it. So which is 0.157. 0.157. Okay. So this is actually the quality. Quality is a dimensionless quantity. There is no dimension because this is the ratio of mass, right? The mass mg divided by mt. So that's why it's all the units cancel out. So there is no unit of that. This is just a constant value. Okay. So this is your number B. Now what is number C? The enthalpy. So if we calculate the enthalpy, you can see from here. Yes, so this is the enthalpy equation. H equal to Hf plus X Hfg. Yeah. So that means H equal to Hf minus X Hfg. So that is also very easy to calculate because we know X, we know Hf. Hf is 31.18. 18. Okay, minus 0.02 times. So Fg means Hg minus Hf, right? So Hg minus Hf, which is 31.18 minus 0.02 times. So G is 241.14. So minus 31.18. So all these giving me 64.1. You can use the enthalpy unit. Okay. So this is our enthalpy. At the end, we have to calculate the Vg. Okay, that is the D. So Vg is mass of the vapor times the volume of the vapor. Okay. So the total this is your mass of the vapor. You already know that is your 0.628 times Vg your 0.12355. That is giving us 77. So if you convert it to cube or you can make it a liters, it's up to you. So this is 0.0776. So 0.0776 meter. Okay, 0.0776 meter cube. So we solved two problems. I think it's very easy. So it is easy for you to understand. And we have a video after that here. So it is a details way, very calm and quiet way. We talk about how much. So this is about 14 minutes. We explain one problem about 14 minutes. That we cannot do it here. So that's why we provided you a separate video. I think it will be helpful for you to understand. All right. We don't have much time in our hand. So there is a superheated vapor is a very easy to, but I think that is the last one. I think I can go in the next lecture. This one today I don't want to go. That is already have given, like, and how did you calculate it? Just a second. Sorry, somebody asked me a question. Let me answer this question. Yes.
Will this slideshow, will it be uploaded to
Yes.
UTS Online or Campus
Is already
or whatever it's called now?
yes, it's already uploaded. This is
Okay.
already uploaded.
All right.
And there is one correction there. So I'll make a correction and I delete the previous one and put it here. The deadline is wrong for your assignment submission. Your lab report submission is wrong. So I'll correct it and upload it. But if you download it, it doesn't matter because no
Okay.
other contents will be changed. Only the date will be changed. But the date is available in the subject outline. So don't worry. You don't need to see this one.
Where are they on the?
Maybe
on
the third or fourth slide.
Okay.
So it's October last year, so you can easily see that. It's a back
No,
date.
but where? Oh, sorry. Never mind. I found it. It wasn't there earlier. Okay. Never mind.
Okay.
That's all good.
Okay.
Thank you.
Yeah, it was not earlier because I did not publish it. So now I have published it and now you can get it. Okay, what
Okay.
I was going
Thank you.
to show you. Yes, someone asked me question. How we get the MG? Okay. So MG is we are getting from I should mention it. How should I write? Okay, I'm taking it here. Okay, sorry. FG. So you know the X equals mg by mt. Now mg equals x mt. Okay. So now you know mt is a 4 kg and you know x. X is, what is your x? 0.157. We already calculate the quality. Here. Here. So we have the x here and we know the mass 4. So that means 0.157 times 4. This is our this value. Okay. Okay. Next time when I do this math, I'll get a clean paper and then I can calculate it. It is very clumsy, so I should not do that. Next time I can do it. All right. So it's already time's up. If you have any questions or anything about the subject or any other things, just you can tell me now. And officially now the class is finished. I can stop recording. Is it recording or not? I stop recording. Yes. Do you want to stop recording?